Hi, here we are, back for part 2 of protection circuits. We left off part 1 at the end of electromagnetic interference. Here we are at the beginning of part 2. We'll move on to electrostatic discharge. Right. So ESD, most of us are aware of the phenomenon of electrostatic discharge after being shocked at one stage or another with the characteristic crack that occurs at the point of discharge when reaching out to touch some object. However, your body does not provide a good measurement of static electricity. It needs about 4,000 volts to feel anything, and this voltage is much higher than many electronic components that can withstand. The components of active devices most likely to fail are some transistors and integrated circuits, usually those from the 4000 or 74C families, metal oxide semiconductors, and complementary metal oxide semiconductors. So we know what electrostatic discharge is. We've talked about this in depth. But as a quick recap, right, a static charge builds up on your body or on some other item. It can build up via friction. When we get that friction build up, we'll get a charge build up on an object. That means that we have ionized particles building up on the object itself, and when that object comes into contact with something that is of a different potential, a different charge, different voltage, then we're going to have current flow, because that charge will flow from one to another, from positive to negative. So we could have a negative charge, negative electrostatic discharge, negative electrostatic charge, or a positive electrostatic charge, and it's going to jump to a different charge. Right, how's it generated? A common way of generating static electricity is by separating two different materials which have been in contact with each other. This method of static electricity generation by friction is called triboelectric charging. I'm not going to read the rest of that. You can read it. We've talked about how electrostatic charge is generated. I mentioned it on the last slide. Generally friction between two objects. All materials are sources of electrostatic discharge. They are lumped together in what is known as the triboelectric series, which defines the materials associated with positive or negative charges. Positive charges accumulate predominantly on human skin or animal fur. Negative charges are more common on synthetic materials such as styrofoam, plastic cups. You would have seen this. Balloons. Balloons are pretty good for static discharge. Synthetic materials that carry static. Trampoline is a great one, right? The nylon mat of a trampoline will pick up shitloads of static. The amount of electrostatic charge that can accumulate on any item is dependent on its capacity to store a charge. For example, the human body can store a charge equal to about 250 picofarads. This correlates into a stored charge that can be as high as 25,000 volts. Yeah, weird numbers there, right? We've done a bit more since the last time we would have looked at static discharge around capacitance and that kind of thing. So 25,000 volts, 250 picofarads. That means at a very high voltage, a very, very high voltage, a very, very small amount of energy, 250 picofarads. So picofarad is 1,000 times less than a microfarad. So tiny amount of energy at a very high voltage. The voltage is why it hurts when you get that shock, but 250 picofarads is why it doesn't do any significant damage to you. How does ESD damage electronic circuitry? ESD is a tiny version of lightning. As the current dissipates through an object, it's seeking a low impedance path to ground to equalize potentials. In most cases, ESD currents will travel to ground via the metal chassis frame of a device. However, it's well known that current will travel on every available path. In some cases, one path may be between the PN junction on integrated circuits to reach ground. This current flow will burn holes visible to the naked eye on an integrated circuit with evidence of heat damage to the surrounding area. One ESD event will not disrupt equipment operation. However, repeated events will degrade equipment's internal components over time. Alright, so what are we saying there? Remember, when we bring those two things together, whatever those things happen to be, when we bring those two things together that of dissimilar charges, then we are going to create a potential difference. So current can flow from one side to the other. It's going to flow. It wants to flow down to a low voltage. If we have a high voltage static, it wants to flow to a low voltage. If we have a negative voltage static, it wants to go to a higher voltage, I guess. And it'll take any path that it can get. If it happens that we have electronics in the way of that circuit path, then it's going to go through them. And although I said 250 picofarads, for example, the human body can hold, doesn't cause us too many problems. A small amount of energy like that with a very high voltage can create problems for an electronic device. Okay. This figure shows a scanning electron microscope picture of a 6 amp MOSFET destroyed by a 1 kilovolt charge. Damage is called ESD damage or gate breakdown. For this reason, ESD must be taken seriously, and the total prevention of ESD is the only policy. Yeah, so this is, as it says, scanning electron microscope, so very, 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 very zoomed in. That probably wouldn't be visible to the naked eye. And here are some more pictures. Here are some more pictures that are of that kind of damage. Obviously on this one here, pretty massive. Again, visible to naked eye. This one's visible to naked eye. These ones maybe not so much. You have to get 5,000 times magnification to see that. And over here as well, we've got some magnification to see that damage. So we may have an immediate failure, or we may cause intermittent faults, or some sort of delayed breakdown, or increased maintenance intervals. To be honest, probably a delayed breakdown or intermittent faults are actually worse than an immediate failure. An immediate failure is generally easy to diagnose and repair. An intermittent fault may not be. There's nothing worse than going to a job, going to a site, and telling you that the equipment did this or that, and you turn it on and test it out, and you can't find anything wrong with it. You spend a couple of hours mucking around with it, and then you leave, and a couple of days later they ring you again, it's doing the same thing. It can be very frustrating to chase down intermittent faults, not least because often you don't even know which component is faulty, so you can't even guess and replace stuff. Can't even go, well, obviously this piece of equipment is faulty, it's not doing it now, but I'll replace it anyway. You don't know which piece of equipment is faulty. All you know is the machine doesn't work sometimes, but apparently doesn't do it when I'm there. So how does ESD occur? Well, we've all felt it, but the most important one that we need to be aware of in terms of electrostatic protection is electrostatic discharge from the human body. Factors which affect the magnitude of the ESD produced are the speed of separation, types of materials separating, and the relative humidity of the workplace. So the faster the flow, the higher the static potential produced. In the same way, the faster the separation of materials, the higher the potential. Type of material, yeah, obviously different things can generate different voltages, and they will generate different voltages when touched and rubbed against each other. So certain materials are more susceptible to creating static with other materials. And the humidity in the air has a strong effect on electrostatic voltages. When the air is very dry, static is easy to produce. If the humidity is high, over 50%, then the moisture in the wet air creates a little bit of moisture on surfaces, which creates leakage paths that can drain away to earth. So essentially what we're saying is that the moisture in the air and moisture on surfaces will create a circuit path for our static to bleed to earth, to be earthed. So the drier the air, then the more ability for static to remain charged on a surface. Alright, here's a list of our objects that will take a positive charge and objects that will take a negative charge. Obviously the biggest charge we're going to get is between something that will take a positive charge and something that will take a negative charge, because then if I get 2000 volts positive over here and 2000 volts negative over here, then they are 4000 volts between them. So which is why human skin as a positive, we get our biggest shocks against synthetic materials, these ones over here, because when we touch those, we've got a positive voltage, they have a negative voltage. Here's a little list of voltages that we may build up on our body, and the types of things that we might do to generate those. I won't go through them. You can pause the video and have a quick look if you need to. Okay, other sources of ESD damage: troubleshooting electronic equipment or handling of printed circuit boards without using an electrostatic wrist strap. Yeah, I mean that's the same. We're discharging the static from our body through the electronic device, but obviously it's more prevalent if you start opening up electronic equipment and handling the boards and the devices, and you're not using electrostatic wrist strap, then the relative danger of you discharging your static through a sensitive device massively increases, clearly. Placement of synthetic materials on or near electronic equipment, so the potential for static to build up there is greater. Rapid movement of air near electronic equipment, including using compressed air to blow dirt off printed circuit boards, or circulating fans blowing on electronic equipment, or using an electronic device close to an air handling system. All of those things are very common. Electronics people often use compressed air cans to clean things. Circulating fans on electronic equipment, we've all seen those, right? Every computer that you've ever seen has a fan on it that sucks air into the case and blows it around to cool the electronics down. How do we measure electrostatic voltage? Well, the short answer here is we use an electrostatic voltmeter, which has the ability to do that. It can measure thousands of volts. This is a fairly specialized piece of equipment. I've never come across one. I'm aware that they exist, but I've never seen one, and I would imagine only specialized people who do this kind of stuff will have them. You are probably never going to see one, but if you do, this is what it is. How can we prevent it? Keep all synthetic material at least 10 centimeters away from our electronic equipment. When cleaning printed circuit boards, use a spray labeled as non-static. Always wear a wrist strap if you're touching electronic equipment, if you're opening electronic equipment and touching the boards. Treat carpets and floors with compounds that reduce the buildup of static charges. Use static floor mats, and make sure the grounding system for equipment has a low impedance for electrostatic currents to dissipate to an earth reference. Look, they're all pretty straightforward things. Most of them are fairly expensive though, like treating carpets and getting mats and stuff. These are things that a company would do. We're not going to do that ourselves unless we're running a business that's dealing with electronics on a regular basis. Circuit protection for electrostatic discharge. The main function of an ESD protective device is to enable ESD that enters a device to escape to ground. If there is no protective device, ESD which has a voltage of several thousand volts will be applied directly to the semiconductor circuits. When an ESD protective device is installed between an external interface and an IC, in order to protect the IC, the input to the IC will be grounded via the ESD protective device, enabling ESD to escape to ground. What does it mean though? What does it mean? We can see in the pictures here, right? We have a protective device here so that when higher voltages come through, this will open and provide a circuit to ground. It'll be a voltage dependent resistor. So when a certain voltage threshold is exceeded, maybe we would use some sort of Zener diode. We know that a Zener diode in the reverse bias position will conduct when it goes over a certain voltage. So if we had a Zener diode in here that is designed to conduct when the voltage along here exceeds a certain level, that level that's going to damage the IC, then it will conduct and it just connect to ground. That'd be pretty simple way to do that, right? In a normal situation, then our Zener diode, or whatever that device may be, but a Zener diode in our example will be a high resistance. It will be an open circuit, so data will just flow through to the IC, and the Zener diode does nothing. That's it. That's the last slide. Right. Our code, I said it was a 3-digit code. You should have got the first digit off the previous video. The next 2 digits are 96. So if you wrote down the first digit on the last video, the other 2 digits are 96. You now have the 3-digit code required to complete the test for this topic. That's it. That's the end. Thank you for joining me.